This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on exponential functions. We're going to start by looking at f of x equals 3 to the x. This is not a polynomial. This behaves a little bit differently than a polynomial. So let's plug in values for x and see what we get for the corresponding y values. If x is 0, 3 to the 0 power is 1. Remember, anything other than 0 to the 0 power is 1. 3 to the 1 is 3. 3 to the second power is 3 to the ninth. 3 to the negative 1 means 1 over 3 to the first, which is 1/3. 3 to the negative 2 means 1 over 3 squared, or 1 over 9. So we have 5 points here for this function. And we can go ahead and graph them and see how it behaves. Now recognize we'll have an answer for 3. 3 to the third is 27. 3 to the 4 is 81. 3 to the fifth is 243, so we can keep plugging in larger and larger numbers into this function, but it will be difficult for us to see them on the graph. However, as we plug smaller and smaller numbers in, 3 to the negative 3, 1 over 3 cubed, 1/27th, 3 to the negative 4, 1 over 3 to the fourth, 1 over 81, etc., those numbers just get closer and closer to 0. So we will have a horizontal asymptote here at y equals 0, whereas this is going to keep growing very, very quickly on that side. So that's what the function looks like as we connect the points. And from this we can identify the domain and range of the function. Domain, what are values that are fair for us to plug in for x? We can plug in large numbers. 3 to the 100th power is a very large number, but x is fair. 3 to the negative 100th power, 1 over 3 to the 100th power, very, very close to 0. So the domain could be anything, but the range, you'll notice, are values that are always greater than 0. So as we say, this domain, all real numbers, so from negative infinity to infinity, range, there is no way for us to get negative values for y. So our range will consist of numbers from 0 to infinity, not including 0. And that will be the case for this function, f of x equals 3 to the x. Now let's take a look at one that's going to require us to do some transformations. We're going to take g of x as 2 to the x plus 3 minus 4. We want to break this down into various pieces so that we can construct the graph. We're going to start by constructing the graph of 2 to the x. And then from 2 to the x to 2 to the x plus 3, that would be g of x plus 3, sort of. That's going to require us to shift it 3 places to the left. And then minus 4, of course, will be a vertical shift down 4. So we're going to start with the graph of 2 to the x, then shift 3 places to the left, and then shift 4 places down. That will be our process for this. So first, graphing y equals 2 to the x. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second is 4, 2 to the negative 1 is 1 over 2, 2 to the negative 2 is 1 over 2 squared is 1 over 4. So that is my graph of y equals 2 to the x. Now if I want to do 2 to the x plus 3, how does 2 to the x plus 3 compare to 2 to the x? That will require us to shift everything to the left 3 places. Shift this to the left, I have the point 0, 1. Shift it to the left 3 places, subtract 3. The point 1, 2, 1 minus 3. The point 2, 4, 2 minus 3. So if we're going to shift the graph 3 places to the left, we're going to subtract 3 from all of the x values. So indeed, shifting it 3 places to the left will look like this. 0 minus 3 becomes negative 3. 1 minus 3 becomes negative 2. 2 minus 3 becomes negative 1. Negative 1 minus 3 becomes negative 4. Negative 2 minus 3 becomes negative 5. This table, negative 3, 1, negative 2, 2, negative 1, 4, negative 4, a half, negative 5, a quarter, is the table, excuse me, as that moved off. That is the table for y equals 2 to the x plus 3. So if we were to graph this, we could get y equals 2 to the x plus 3. But the last thing we have to do is to shift that table down 4 units. So here's our y equals 2 to the x plus 3. These are the values from the previous table. Again, negative 3, 1, negative 2, 2, etc. The last move we want to do is we want to change that to y equals 2 to the x plus 3 minus 4. So that's going to require me to shift all of these points down 4 units. So the y value, 1 minus 4, 2 minus 4, 4 minus 4, etc. So shifting it 4 places down, there we go ahead and get it. 1 minus 4, negative 3, 2 minus 4, negative 2, 4 minus 4, 0, a half minus 4, negative 3 and a half, a quarter minus 4, negative 3.75. So again, the x column is here, the y column is here. Let's take a look at it. And let's graph those points and see how this is behaving. So those are the 5 points. And again, we could plug in 1. 2 to the 1 plus 3. 2 to the 4 is 16 minus 4 is 14. 2 to the 2 plus 3. 2 to the 5, 32 minus 4 is 28. So we have values for 1, 2, 3, 4, 5, 6. So our domain could be anything, but I want you to think about what the range is. How is this moving? What's the lowest that this can go? That's what our picture looks like. Again, domain all real numbers, but we're never going to get to -4. 2 to a large negative number, so is 1 over 2 to a large positive number, very, very close to 0. A number very, very close to 0 minus 4 is very, very close to -4, but it never actually quite gets there. So our range includes values that are greater than -4. So our range are values from -4 to infinity, but our domain are all the numbers, all the real numbers from -infinity to infinity. Our next example is going to be to construct the graph of h of x equals -2 to the x plus 5, as well as trying to determine what's the domain and range for that function. So what's the process we're going to use? First, I want to graph 2 to the x, because -2 to the x will just require me to put a minus sign in front of these. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the -1, 1 over 2 to the first, 2 to the -2, 1 over 2 squared, 1 over 4. So that column is 2 to the x. My next column will be -2 to the x, so that'll be -1, -2, -4, -1/2, -1/4. So now I have those values. So I have my x column and I have my -2 to the x column. And I'll finish off by adding 5. So here's my -2 to the x column. If I add 5, I've got to add 5 to all of these. -1 plus 5 would be 4, -2 plus 5 would be 3, etc. So here's my column. As I add 5 to each of these, -1/2 plus 5 is 4.5, -1/4 plus 5 is 4 3/4, 4.75. So my x column and my -2 to the x plus 5 column are what we're going to use to graph our first set of points to determine how this function behaves. So there are those two columns, and as I graph those points, it looks like this. And again, we want to think about what's our domain and what's our range. I can plug in numbers. I can plug in -2 to the 4th, -16 plus 5, -2 to the 5th, -32 plus 5, -2 to the 10th, -2 to the 100th. I can do all that, as well as with the numbers back here. So my domain is again going to be all real numbers, but the question is, what is the range? What are my possible y values? So let's take a look at the graph. Looks like this as we connect our points. So our domain indeed is all real numbers, -infinity to infinity. Our range, all of those values are less than 5, mainly because think of this as 5 minus 2 to the x. If you subtract 2 to the x from 5, you're always subtracting some positive number from 5. 5 minus a positive number is never going to get to 5. It'll get close to 5, and it certainly can't go beyond 5. So our range includes those values where y is less than 5 or y values from -infinity to 5. So just a little discussion on how to graph exponential functions. Next, we're going to look at a very important constant in mathematics. Some argue the most important constant in mathematics. It's defined in a sense by this function 1 plus 1 over n to the n. Now let's look at various values of n and how this behaves. For example, if n is 10, I get 1 plus 1 over 10 to the 10th. And the decimal approximation, that should be approximately equal, by the way, is 2.5937. Let's go with a larger value of n. If I go to n is 100, 1 plus 1 over 100 to the 100th power is approximately 2.7048. And let's go with an n of 1,000, so 1 plus 1 over 1,000 to the 1,000, about 2.7169. So hopefully you're getting the idea that these numbers are stabilizing. In calculus, you'll prove that, but the reality is as n gets larger and larger and larger and larger, these numbers converge on a single number. So I'll use the calculus notation to say that the limit as n goes to infinity, and so I've corrected that, the limit as n goes to infinity of 1 plus 1 over n to the n is e, which is approximately 2.71828, one of the most important constants in all of mathematics. So one of our favorite functions is the function f of x, or y equals e to the x. Let's just take a quick look at that graph. E to the 0 is 1, e to the 1 is e. You'll notice e to the 1 is about 2.718. E to the 2 is e squared, e to the negative 1, 1 over e. So this is a very important function that you'll see quite a bit in calculus. All right, we're going to move on to solving an equation. We want to solve the equation 2 to the x equals 16. How are we going to do that? We're going to rewrite that in terms of exponents. What is 16? 4 times 4, 2 times 2 times 2 times 2. 16 is 2 to the 4th power. So we get 2 to the x equals 2 to the 4th. If that's the case, what can we conclude? Of course, x equals 4. Relatively easy for us to do. Next question is a little harder. We have 8 to the x plus 1 equals 32 to the x. Now 8 to the first is 8, 8 to the second is 64. So I can't work with a base of 8, but I can work with a base of 2. 8 is 2 times 2 times 2. 32 is 8 times 4, or 2, 2, 2, 2, 2. So 8 is 2 to the 3rd, 32 is 2 to the 5th. So I can rewrite this as 2 to the 3rd raised to the x plus 1 power equals 2 to the 5th raised to the x power. Then we remember from basic algebra, when you raise a power to a power, we multiply the exponents. So 2 to the 3 times x plus 1 equals 2 to the 5x. If that's the case, then 3 times x plus 1 equals 5x. Distributing, 3x plus 3 equals 5x. Let's subtract 3x from both sides. 5x minus 3x is 2x, 3 equals 2x. Then divide both sides by 2, 3 halves equals x is our answer to that question. And let's take a look at the following. 3 to the x plus 1 equals 1 over 81. Now let's think about 81. 81 is 9 times 9, or 3 times 3 times 3 times 3. So 81 is 3 to the 4th power, and we get 3 to the x plus 1 equals 1 over 81. 3 to the x plus 1 equals 1 over 3 to the 4th. 1 over 3 to the 4th is the same as 3 to the negative 4th power. So we get 3 to the x plus 1 equals 3 to the negative 4th power. If that's the case, then x plus 1 equals negative 4. Solving for x, subtracting 1 from both sides, we get x equals negative 5. Okay, let's take a look at one more question. I have e, as we mentioned before, approximately 2.71828. E to the x squared equals e to the 2x times e to the 3. And we remember, when you are multiplying two common bases, you add the exponents. So e to the 2x times e to the 3 is e to the 2x plus 3. So now we have e to the x squared equals e to the 2x plus 3. If that's the case, x squared has to equal 2x plus 3. And this is a quadratic equation. We're going to solve this by subtracting 2x and subtracting 3 from both sides. And my next line will be x squared minus 2x minus 3 is 0. Now, again, that's a quadratic. We can solve it by factoring. That's x minus 3 times x plus 1 to check. X squared plus 1x minus 3x. That's minus 2x. Negative 3 times 1 is negative 3. So we get x minus 3 is 0, or x plus 1 is 0. Adding 3 to both sides here, we get x is 3. Adding negative 1 to both sides there, we get x is negative 1. And that will conclude this lesson.